rainbows. You've probably seen them in coloring books, comics, cartoons, or even just in the sky. Or when you're watering plants, like when you have a hose on mist and it's a sunny day, well, look what happens. You have a rainbow right here. But the thing is, what is a rainbow? Well, a rainbow is a physical phenomenon. And actually, I can't really touch this rainbow. Like, I can't feel it or anything. It's not like I can get to the end of it and find like a pot of gold or something. So how exactly does it work?
So the most iconic thing about a rainbow is most definitely its spectacular array of colors. But how exactly does a rainbow get its array of colors? Well, we know that the light that a rainbow uses comes from the sun. And the sun's light is also white light. But how does white light make all those colors? Well, white light is actually a combination of all the colors of the visible light spectrum. And so what a rainbow can do, it can undergo a process known as dispersion. Dispersion was discovered by Sir Isaac Newton when he first used a prism in order to split white light into all of its constituent parts. And yes, this is the same Sir Isaac Newton who discovered his 3 important laws of mechanics. So, a rainbow can also do dispersion, but a rainbow uses the small water droplets in the air in order as its prisms in order to create the rainbow. So, what we have here is we have the light that's coming through the window from that direction, and we have a small hole that's cut into this Bristol board, which is in order to make sure that the beam of light is as small as possible for us to see the rainbow as clearly as possible. So what we're going to do is we have the prism, this small triangular prism right here, and we're going to have to use this prism to follow, and we're going to have to follow the light beam all the way down to this paper. So we're going to have to find the light beam, and it's right here right now. So we're going to have to slowly follow it all the way down to the paper, and we're going to have to make sure that the light goes through this prism. But the light's going through the prism right now. The thing is, the angle is also super important. So right now, we actually can't see anything. We can't see the effects of dispersion, and it still looks like white light. Similarly, with a rainbow, if the angle is not right, you actually won't see a rainbow. So we actually have to adjust this angle just slightly in order to see the effects of dispersion. And now we actually see that the white light has been split into all of its constituent colors. So you've seen how we can use a prism to split white light into all of its constituent parts. But how exactly did that happen? Well, before we get into that, we have to talk about an important optics concept known as refraction. So refraction is when we have a beam of light coming incident to a surface and then going into a new medium. So what happens is that the light will bend, and we can represent this mathematically using Snell's law. Snell's law states n1 sine theta 1 equals n2 sine theta 2. So n1 and n2 are the indices, like so, but the index is the ratio of c, which is the speed of light in a vacuum, over v, which is the speed of light in the medium. So then we have theta 1 and theta 2. And theta 1 and theta 2 are both with respect to the normal, like so. So in our case, with a prism, we are going to be using a constant theta 1, which we know, and so we are looking for theta 2. But n1 and n2 are actually both functions of the wavelength lambda. So what we can do with n1 is actually we can just use normal n1 because n1 is going to be air, and the index difference for different wavelengths is so small in air. So it will still be the same. So we arrange this to get sine theta 2 equals n1 over n2, but n2 is a function of lambda multiplied by sine theta 1. And now, what is evident here, if we have a larger wavelength, such as red light, it actually produces a lower index, still greater than n1, which means that the difference between theta 2 and theta 1 will be small. But if we have a smaller lambda, such as blue light, we'll actually have a greater N2, which means a bigger difference between N1 and N2, which results in a greater difference between theta 2 and theta 1. So this is how we can split the white light into its constituent parts. But let's see how that works in a prism. So we can have a prism like so. And then we can have an incident ray of light on the prism. So let's see what happens to the light. So we know red light has an index in glass of 1.5 to 0, and blue light has an index in glass of 1.531. Clearly there's quite a difference there. So how is that represented in this diagram? So what will happen is that the red light will only refract a bit compared to the blue light, which will refract much more like so. And there isn't too big of a difference right now, but that's because it is only refracted one time. It actually refracts 2 times, so we apply the same thing and we get essentially 2 times the difference in the angles. So now get this refracts a bit, but the blue light will refract a lot. So then we get a difference in the 2 beams, which results in a phenomenon known as dispersion.
So now let's put all the pieces together. So first I will be drawing a small rain droplet just to be like a prism so we can undergo dispersion. So we have the white light that's entering, and then this white light will, because of the refraction and the different indices for all the different wavelengths of light, it will actually turn to all the colors of the light spectrum, but we'll just be using blue light and red light to represent both sides of the visible light spectrum. So we have the blue light, which is just also reflects off the back, and then the red light, which also reflects off the back, but because of the different refraction angles, you see that the blue light is actually refracting at a lower angle, whereas the red light is refracting at a greater angle, allowing us to see the red light, but not the blue light. So how do we see the blue light? Well, there's many rain droplets throughout the air, and with a lower rain droplet, we can draw a similar scenario where we also have the refraction and the dispersion and the reflection of light. And this time you can see that the blue light will actually reach your eye because the rain droplet is lower, and it will allow us to see the light, whereas it won't allow us to see the red light. So now let's trace back the images just to see a clearer picture of what we see in the air. So I'm going to draw a thick red line just to represent the red part of the rainbow, and then a thick blue line to represent the blue part of the rainbow. And clearly you can see that the order of the colors in the rainbow will hold true: red, orange, yellow, green, blue, violet.
Thank you for watching, and I hope you have learned something about rainbows. And make sure to leave a comment or suggestion down below, and stay tuned for more videos.